Good morning, everyone. Yeah, my talk is about the Beam Rust sandwich. Before we get started, let's do some housekeeping. You can scan this code if you want to follow the slides on your phone. There will also be some links. Let's hope you don't DDoS my server when you open it now. You can also access the slides after the talk there. Also, we will have a lot of code on the slides, so if you cannot read the code up here, please come a bit closer. If you look like this, trying to make out the code. There are always cats on the slides, so I thought I just put my guinea pig on there to counter the imbalance here. A bit about myself. I'm Julian Köpke. I'm a software engineer from Munich. I've been coding for over 20 years, but I'm relatively new to the Beam, so I just discovered Elixir like 3.5 years ago. But I'm happy that I found it. And yeah, you can follow me on Bluesky, or you can also subscribe to my RSS feed if you're old school. There we already go with DDoS. I see I have 10 visitors. Everything is a bit slower now. Yeah, 2 years ago I started a new job on a startup, exciting startup, and we built an app for parsing, rendering, and analyzing PCB layouts. That's what you can see here. We used Rust mostly for performance and safety, and because everything is SaaS nowadays, we also had to bring it to the web. So I created a LiveView application and tried to integrate it somehow. And what I learned there, some of the things I want to share with you today. We will have 4 parts in this talk. First, I'll do a bit of general comparison of Elixir and Rust. Then we will look into Rust on the Beam. In the third part, we will look into how we can use Rust in the browser. And in the fourth part, how we can put everything together to a nice sandwich. Let me know a bit about you. Let's do a show of hands. So please raise your hand if you have coded a Phoenix LiveView app before. It's amazing, so almost all of you. Oops, that was one too far. Hand up if you have written code in Rust. That's around half of you. And if you have compiled something to WebAssembly, okay, that's even less. Great, so I think I've prepared the right talk for you. Let's look into Elixir and Rust first. There are some similarities. Maybe it's coincidence that both languages appeared in 2012, at least according to Wikipedia. I wasn't sure. Elixir, some sources said 2011, but let's just say they are the same age. They both built on a great tooling and ecosystem because they're modern languages, and they are both built with safety in mind, even though they have very different approaches of reaching this safety. And my favorite feature of both languages is that they have a very effective way of not having to manage shared mutable state, which is great, even though they have completely different ways of doing this. And talking about different ways, the differences between Elixir and Rust are pretty grave. So Elixir compiles to the Beam, obviously. Rust goes directly to machine code. The Beam is garbage collected, and the Rust has a borrow checker, which basically makes sure during compile time that all your memory is allocated and deallocated, and everything can be baked into your binary. So nothing during runtime. The typing in Elixir, we heard it today, is work in progress. I'm actually looking forward to having more support there, but it's not a statically typed language. And Rust is. Everything is super strict. And mutability on the Beam, as we all know, is not a thing. In Rust, you can do mutability, even though it is explicit. So you have to mark everything you want to mutate as mutable. And then the borrow checker will make sure that everything that is mutable cannot be read by anything else. So you only can have one write access or multiple read access to any variable. And Elixir, of course, is functional. That's why we love it. The Rust is not very functional. Some people say it has some functional traits, even though I think the most important features of functional programming languages are not there in Rust, so I would call it imperative. But what makes this integration so great then? Rust is actually the butter on our beam sandwich. It makes it fills the gaps and makes it possible to use the beam in areas where we maybe not have a good way to reach otherwise. So first of all, it can compile directly to WebAssembly. So we can actually run it in the browser, which we cannot with Elixir. And it's blazingly fast. This was, I think, in 2019 already. There was an article by Discord how they used Rust to scale their Elixir server to 11 million concurrent users, which is pretty impressive. So it's a nice way to fill the gaps when you maybe notice that the beam is not fast enough anymore, or when you want to reach a target that you cannot with Elixir. So let's look into Rust on the beam. This is our Phoenix LiveView server, just a little overview. It runs on the beam, and we want to place a little NIF, a natively implemented function, inside of our application, so we can call it from our LiveView, and that should be written in Rust. To do that, first of all, we have to add a dependency. There's a nice package called Rustler, which gives us everything we need. So we add this to our mix.exs in Elixir, and then we can get started. We will have a shell command called mix_rustler.new, which generates the Rust boilerplate, the project inside of our application. And in Rust, you will have a cargo.toml file, which is basically defining the dependencies similar to the mix.exs file. And there you have your name, and you also have a dependency on Rustler, so basically the other direction. Next up, we will implement a tiny function. The add function, it takes 2 integers and returns an integer, which is just the sum of those two. And above that function, we will annotate it with a Rustler NIF, which tells our compiler that this will be used from our beam directly. And below we call Rustler.init, so we can bind this to an Elixir module. So we also know in the other direction how to call it. And then, of course, on the Elixir side, we have to hook this up similarly. So we create a module in the Elixir side, and we just use Rustler. Magic happens. We define our add function with the same shape, and we just implement a NIF error, which will return by default if the NIF is not loaded. But if it gets loaded, this will be replaced by the actual call to our Rust function. And now we are already almost done. We just have to hook this up. So as an example, I just dropped it right into the Heeks template. We call sandwich.backend.add 1,2, and we will get a return value of 3, which is calculated by our Rust code, which is great. So backend is already done. It was really simple, and I'm actually surprised how easy it is already. If you want to learn more about NIFs, the next talk is for you. I think Ricardo will use C for his talk, but in general, most of the things you have to be aware of when you are implementing NIFs generally apply also to Rust. Let's look at Rust in the browser next. This is the harder part. So let's look at a little overview. We have our browser. In our browser, in a Phoenix LiveView application, you have your JavaScript with the LiveView client running. And what we want to do from there is we want to call a WebAssembly module, which we will also deliver to the browser. And this module we want to implement in Rust. Let's have a little overview of WebAssembly in general. WebAssembly is a platform-agnostic virtual assembly format. It reaches near-native performance, and it can be targeted by many languages. For example, Rust, C, C++, Kotlin, Dart, or Camel. There are many compilers that can compile to WebAssembly. It's completely sandboxed, and the specification is formally verified, which means you cannot call anything outside of your WebAssembly. So everything you want to call, you have to pass in, and they're pretty sure that you cannot escape the sandbox. There was recently, there were a few security issues found in the specification, but they were fixed quickly and should be pretty safe in general. But because you don't have a like a standard library, there are standards to use this in a useful setting. For example, the WebAssembly system interface WASI is a standard to build system applications using WebAssembly. And one example that implements the standard is WasmTime. It's a runtime which is written in Rust. And for browser applications, usually we need some JavaScript glue code, so we can call a JavaScript function from our JS code, and that will pass this call into the WebAssembly. And to generate this glue, in Rust we use WasmBindGen, that basically looks at our annotations in the Rust code and just generates all the JS we need, and then we can import this from JavaScript. I will show it to you later. WebAssembly is actually used by a few quite big projects already. So, for example, the Unity game engine is one of the big users. They basically can run their games in the browser using WebAssembly. Figma, they started, I think, with C++, and with Mscripten they compile everything to WebAssembly. Flutter can already build your Flutter apps to target the browser. They are also recently switched to WebAssembly, and the set editor uses it for its plugins, which is actually a quite interesting way to make use of this. So, how do we get our code, our Rust code, to WebAssembly? Here on the right, you see the first use case we had before. The beam calls into our target function, and we do something. But now we want to have some shared functionality. So we need to pull out the shared functionality into a shared module, which is in the middle here. And then we add another shim on the left, which we can call from our browser. So basically, those two functions will, on the one side, be implemented to be called from JS, and the other one from the beam. And they both call into the same function to run our business logic. And then the right box will be packaged as a on Linux as a SO file, so it can be linked by our beam. And on the left, it will generate a WASM file and some JavaScript, so we can deliver it to the browser. To do this, in Rust, we have to define our targets. So in every dependency, you can specify for which targets it should be used. And our Rustler dependency, when we are running on Linux, of course, this should only be compiled on Linux, because Rustler will not work in WebAssembly in the browser because there's no beam. And our wasm bindchain dependency, which should only be used for WebAssembly, this should not be compiled for the beam, so we target it only for the WebAssembly 32 dependency. Then we pull our add function into this shared module. This is basically unchanged, just with a new module here. In general, you can, or you would, pull out complete modules or libraries and have a shared module for your business application that is compiled for all target platforms, and then have one library for WebAssembly, one library for Rustler. But to keep it simple here, I basically inlined everything. It's all in one file, but it still targets different platforms in the code directly, function by function. So the next step, we implement this shim function. So the add function will just pass the call to the shared add. And here also we have the target OS Linux, and we have our Rustler NIF annotation. So Rustler knows this is something I can call. And we also annotate the Rustler init call with a Linux only, because if you try to run this on WebAssembly, it will just explode. And then to actually call something out of our WebAssembly, we will hook up the alert function from the browser. So we will tell the Rust compiler, please generate a function I can call from outside, which should be hooked up to the alert function. So when we call this from inside of WebAssembly, we will be able to generate a browser alert and actually get something out of our WebAssembly. Then next step, we would use this function. So we implement the add function for WebAssembly. Again, we call our shared add function, store the sum in a variable, and then we call the alert function with a nice format call here, so we have a bit more meat, that we actually know what's going on. And with this wasm bindchain hook, this will generate the hook we can import from JavaScript then. And before we can go to JavaScript, we want to build all of this, because in JavaScript we want to import this, and right now there's no JavaScript code, and we don't want to handwrite this. So we just write a small mix task. I called it wasm, and it will just call to the wasm pack executable on our platform. It will generate all of the JavaScript files and the WebAssembly packet, and then we just copy this to our Phoenix assets. So in the assets we can link it in our JavaScript app.js, and we can also access it later from the browser by downloading it, by querying the web server to give us the WebAssembly packet. And now we are ready to use this in our JavaScript. In the first line, you see the import. This is the generated file we import, and from the import, we get two functions. The add function, that is what we defined, and initSync is a function to initialize your WebAssembly module. And then we implement a load function that downloads the WebAssembly packet and calls the init function with this downloaded packet. There are different ways to do this. Actually, you could also use esbuild directly in Phoenix to generate all of this, and it will bundle everything into your app.js. But the WebAssembly will be base64 encoded, and it will have to regenerate this huge thing every time you make a change. And I noticed during development this can be quite inconvenient, because if you have a big WebAssembly bundle, your hot reload will take seconds and everything becomes a bit sluggish. So I preferred this this way of initializing it. And I put a link here. There's an interesting article about the different ways of initializing WebAssembly. Yeah, and then in the last line we add an event listener, so we can actually call our add function from the browser. And here you can also see we have to convert our types, because in JavaScript everything is a float, and in Rust we defined this as an integer, so we convert it to big int, which will be then represented as a 64-bit integer in our Rust code. And now we can run this, click our button, which we implement here, that dispatches our click event, and it will go through the WebAssembly code and call this alert function with our addition. Now we also have a working front end. I hope you're not asleep yet. I hope this didn't bore you. Now let's get to the integration of all of this. Finally, we have the sandwich. On the bottom, we have our Phoenix LiveView as before, and on the top we layer the browser. And what we added now is the nice sandwich in the middle. The WebAssembly, the WebSocket connection on the left. So basically, our LiveView client will connect through a WebSocket to our Phoenix application, and they will communicate over this socket. And we want to make use of this because we don't want to have a separate overhead communicating from WebAssembly, and it's actually quite nice to use this event-driven style. So yeah, the Phoenix LiveView provides both the app.js and the WebAssembly, and then it will serve as a server for both. And we will just pass through the events from the WebAssembly code to the server. So we want to keep the JavaScript glue lean, so we don't want to have additional logic in there. We just pass events through in both directions. In Phoenix, we can use the handle event and the push event functions to deal with this. And depending on the framework or the libraries you use for generating your WebAssembly, in our example, we used Bevy ECS. There you have a nice event writer and reader, so you can treat those events in a similar way. Okay, now let's get to the even more interesting part. I have prepared a live demo. We will replace the add function now with a fully functioning Lua interpreter. So we have a bit to play around. And everything else is pretty similar. So what you can see here is our text input field where we write the Lua source code. And when we press execute, we will do two things. We will send this as an event to our backend. It will be executed by the Rustler implementation of our Lua VM. And it will return the resulting string back to our front end as a Heeks template string. And it will print here as Rustler output. At the same time, we will also call our WebAssembly code and do the same thing, run the same interpreter, and execute in the browser. So now, when I implement my main function, hello codebeam, and I press execute, you can see this comes immediately from our browser implementation, and you can also see the response from the backend. Wait, becomes more interesting. Now, I kill my Phoenix. You can see the terrifying red box in the corner. So our server is dead, the connection is not there anymore. And now, when I do something and press execute, it will still execute the code in the browser, but you can see the Rustler output does not refresh anymore. So you can still run things in the front end without the connection. There's no latency, there's no overhead. So you can actually implement things that are heavy in the browser and do not always have to rely on the round trip to the server. Now you can clap. So, to conclude what we have learned so far, let me switch back to my slides. Before you go and rewrite everything in Rust, this is useful when you have existing Rust code, because you can just drop it into your Beam or you can just drop it into your browser. You can also use it when Rustler is a way to speed up what you have to process. For example, when the Beam is too slow because you have to do some heavy number crunching. You can use it when the performance matters and you want to be really responsive in the browser and you don't want to implement your stuff in JavaScript. For example, when you implement a game, this would be a nice way to just deliver the game client as a WebAssembly packet to your browser, and you still can run the game logic in the backend to verify that everything that your clients are doing is valid. You could also use it to load share. So if you want to mine bitcoins on your homepage visitors, browsers, you can just send them a heavy package and they can process things there. Or you can use it for security, for example. If you want to encrypt stuff in the browser and then send encrypted data to your backend, you don't have to deal with the raw data anymore. You don't have to worry about encryption there. So you can basically implement end-to-end encryption with the browser. This is where this approach works really well. But there are also drawbacks. So let's look into the ergonomics. Not that type of ergonomics, but speaking about how easy it is to use the language. There's a quote by Jonathan Blow. He said, "Rust makes the assumption that all code is production code." And this resonates very well with me because you can feel it. There's no way around the borrow checker. It will always get you. It will make sure that your program is memory safe when it passes, but until then you have to make sure that that you write valid code. It's just a checker. It doesn't do the memory management for you. So you always have in the back of your head, you have the memory management, and you will have to think about it, especially when you're used to writing GC languages like Elixir. And then there's concurrency. I found this amazing post by Haley on Bluesky, where there was a post from some Rust community about fearless concurrency. But we all know concurrency should be done on the Beam. And it can be quite challenging to do in Rust. So I fully agree with this sentiment. And then there are also a lot of reports in the internet where people started doing things in Rust, but actually they were not happy with it, and maybe a few years later they decided this is not the right language for me. One very prominent example is Richard Feldman, the creator of the rock language. he started everything with Rust, and at some point he decided to switch things over to SIG because it just suits what he's doing better. Because sometimes it's not the best language to use everything. And yeah, I linked a few other articles here that are pretty interesting. And for me, this is proof that if you fail doing Rust, it doesn't have to be a skill issue. You don't have to be worried that you're just not good enough. You're just a bad developer. It's just it doesn't fit everywhere, and you should be aware of it when you pick it. So what are alternatives we have? One, popcorn. I think we will have a talk about this in the afternoon. It's a nice implementation of the Beam, the Atom VM, like a re-implementation of the Beam, but it's compiled to WebAssembly and it runs in your browser, so you can actually execute the Elixir code in the browser. So it does not give you all the speed up benefits, but it's another interesting way of shipping and running code in the browser. Everything that I showed you, you can do with SIG too. So there's also a backend called Sigler, which is basically doing the same as Rustler. And you can also compile SIG to WebAssembly, so you can run it in the front end. And then there's WesMax. That's an integration of a WebAssembly runtime that is embedded in Elixir. So it also uses Rustler, but you can actually execute your WebAssembly code in the backend. So basically every language that compiles to WebAssembly, you can call from your Elixir backend by using WesMax. This is an interesting approach. You will lose a bit of performance there, but you will also gain some portability, and it's definitely worth a look if you're interested in those things. Yeah, and then before I let you leave, whatever road you take, I have this slightly altered quote: "The reasonable developer adapts himself to the world. The unreasonable one persists in trying to adapt the world to himself. Therefore, all progress depends on the unreasonable developer." You can scan this QR code to get to the example project that I showed, so you can also run it. There will be also a link to the slides. It should be public since today. And that's it. I would be happy if you can provide some feedback for this talk, and thank you for your attention.
That was a super cool demo.
Thanks.
Questions?
So when you show that example that you are compiling to WebAssembly, but also compiling it directly and running it with Rustler, aren't you worried about the floating point operations if you do that, that they will not be the same result? For example, that's why Rust doesn't let you do constant expressions with, like, I don't know, square roots or trigonometry.
Mm-hmm. Yeah, I mean, you're targeting a different architecture, so it could be, but I think since you are using the same IEEE standard, the operations itself should return the same result. But don't quote me on that.
Yeah, I'm not sure either. That's why I was asking.
I have a question for you. Someone wrote me on Bluesky asking if I can mention this, and I really liked it. I don't have a name for this stack yet. And he said in his team they're also doing this, and he suggested the name Runix. So Rust plus Phoenix equals Runix. What do you think?
It's a tricky one. We'll have to workshop that hallway track.
Yeah. Yeah.
More questions?
Thank you for the talk. When you explained how to put in assets WASM file, there was one JavaScript file, but didn't explain what is in this file.
Very good question. It's the file which gets generated by our. Let me show the slide again. Oop, that's the wrong one. There we go. The WASM bindgen. So this generates the glue code. So you can call the function from your JavaScript, and it will translate this call into something that is understood in WebAssembly. So it will transform all of the stuff, copy the variables you pass into a format that can be used in WebAssembly. And all of that is auto-generated. It's not very readable, so it works with like arrays of integers and does very interesting things. But you don't have to worry about it.
You have 64 and WASM is 32.
Yeah, the WASM 32 is basically the standard that is used everywhere in the browser right now. But that's the size of the the operations, and you can still have bigger numbers.
Yeah, it has more to do with the memory that you can address. There is WASM 64, but it's not something you'd see in browsers right now. Any more questions? Have you seen any attempt to bring more WASI type features like the WASM component model?
Specifically for Rust or?
For Rustler or any other sorts of integrations?
None that I can think of now.
Context being that you see these are integers passing back and forth. You can do more data types, but you have to define an ABI because WASM internally is just integers. So you map it to something. That's what bindgen does, and that's also what the WASM component model does, and WASI to some extent.